This week on the show, we cover the fact that software will never fix Spectre-type bugs. We also present a proof that Z is Turing complete. We show you managed jails using Bastille. New versions of NetData are out. We also cover a little bit using grep with DevNull, as well as using Gmail with Mutt. And if you think, oh wow, then you should watch this episode of BSD now. BSD Now, episode 288, Turing Complete Z, recorded for the 6th of March 2019. Hello, I'm your host, Benedikt Reuschling.
And I'm Alan Jude.
Welcome back to our BSD Now episode for this week. We have great headlines for you this week, as always. This one is called Google Software is Never Going to Be Able to Fix Spectre-type Bugs. Yes, It's still haunting us.
So this is based on a paper they presented, I guess it doesn't say where, but Spectre is Here to Stay, an analysis of side channel attacks and speculative execution. But the article goes on to say, researchers from Google investigating the scope and impact of the Spectre attacks have published a paper asserting that Spectre-like vulnerabilities are likely to continue to be features of processors, and further, that software-based techniques for protecting against them will impose a high performance cost. And whatever the cost, the researchers continue, the software will be inadequate in some ways, and some Spectre flaws don't appear to have any effective software-based defense. So it might not be worth all the performance penalty. As such, Spectre is going to be a continued feature of the computing landscape with no straightforward resolutions. The discovery and development of Meltdown and Spectre attacks was undoubtedly the big security story of 2018. First revealed last January, new variants and related discoveries were made throughout the rest of the year. Both attacks rely on discrepancies between the theoretical architectural behavior of a processor, what the processor says it's going to do, the documented behavior that programmers depend on and write their programs against, and the real implementation. So the processor says, when you do this, I will do that. But really, it's when you do this, I'm going to try both and see which one works and then take the one that finishes or whatever. But that might have this side effect where certain information gets left over here where somebody could go read it. Specifically, modern processors all perform speculative execution. They make assumptions about, for example, a value being read from memory or where an if condition is going to be true or false, and they allow their execution to run ahead of the actual decisions and assumptions. If the assumptions are correct, the speculated results are kept and the computer is faster. If it's wrong, the speculative results are discarded and the processor redoes the calculations going down the other branch. Speculative execution is not an architectural feature of the processor. It's a feature of the implementation, and so it's supported or supposed to be entirely invisible to any running programs. When the processor discards the bad speculation, it should be as if the speculation never happened. But sometimes there are footprints left behind. What the Meltdown and Spectre researchers found is that the speculative execution isn't entirely invisible, and that when the processor discards the speculated results, some evidence of the bad speculation is left behind. For example, speculation can change the data held in the processor's cache, meaning that if you try to read two different variables, one of them might end up being much faster because it had already been loaded into the cache. And you can use that to maybe learn something about what else is happening on the computer and so on. Programs can detect these changes by measuring the time it takes to read data from memory. If it's faster than this time, then we know it had to have come from the cache and not from memory, or it had to come from the disk and not memory, or whatever.
So
anyway, there's lots more detail in the article, and then even more detail in the paper with all of its sections.
Yeah, and a lot of authors that contributed to that. Next one, we have a proof actually that Unix utility Z is Turing complete. Oh, that sounds interesting. So we dig into it. Many people are surprised when they hear that Z is Turing complete. How come a text filtering program is Turing complete, they wonder. Turns out Z is a tiny assembly language that has a comparison operation, a branching operation, and a temporary buffer. These operations make Z Turing complete. So the author of this article here is first learned about this from Christopher Blaze, I think. This proof is by construction. He wrote a Turing machine in Z. There's a Z script here to download. And as any programming language that can implement a Turing machine is Turing complete, we must conclude that Z is also Turing complete. So they offered the introduction to Turing machines and a description of how the Z implementation works in this article, also in the blog post. And here's an example program for his Z Turing machine that increments a binary number. The program has the initial tape configuration on the first line of the program and the program itself below it. And in this example, the initial tape config is the binary number 100101111, which is 151. And the program increments it by 1. So here you see the script. And to actually run this program, you save it to a file and pass it to Z via the F parameter, because it's an external file, similar to AWK scripts, and give the example.tm, this is the Turing file, into it to read from. And you get the following output. So this is the final state at the end, reached, end of processing. And this shows us that the state and tape changes as the program is executed. And when that is done, the final state F is reached and the computation process terminates, producing 1001100, which is 152. As a result, as expected. But because this is the first person to realize this, Z is almost a general-purpose programming language. People have written Tetris, Sokoban, and many other programs in Z. Too much time on their hands. Take a look at these. They're linked there. There's also a calculator. And so there's also a nice picture, yeah, because Alan Turing can't believe Z is Turing complete. Nice. And yes, there's a bit more down there for the people who are really into some more Z parts. And there's also a Z book linked at the end if you want to dig more into what Z can do besides being Turing complete.
Yeah. All the things you could do on Z.
Are you using Z a lot?
Only a little bit.
Yeah, because some things are like, I need to add this one line to this file, and I could use a \a addition Z command, but then it's like, well, let's just fire up the editor and just put it there.
Well, call me back when you have 100 files to do it too.
Yeah, that's different.
Yep, Z.
Or deleting stuff from files like empty lines or something, those standard stuff. That's pretty good for Z, yeah. We have news for you, of course, our news roundup, as always, with Bastille being the jail management utility, helping you quickly create and manage FreeBSD jails. This is over at BastilleBSD.org.
Yeah, BastilleBSD.org.
And yeah, they describe what jails are, extremely lightweight containers that provide a full-featured Unix-like operating system inside. And if you have too many of those, I guess it's better to have a management utility, which this tool does. And it features 0 dependencies, template support, highly secure by default, read-only root isolated networks, and target multiple jails, of course. And that's a very nice website for a jail management utility.
Mm-hmm.
Provides jail templates and some cool things where you can just deploy this, and I want to have like a Python environment or a Go programming environment, and then it gets deployed for you. So these are pre-configured templates. Of course, you can have an empty jail that just has the base operating system parts needed. So yeah, this is there. And it provides, of course, the interface to create, manage, and destroy these secured virtualized environments for you. And with the current version, it's still in beta, but still seems to be working well enough so that you can try it out. And you can find the latest source code over at GitHub.
Yeah, it'd be interesting to hear people's write in their results of having given this a try.
Yep. And if you have a lot of machines, then you would also want to have a look at them, what they're doing, or give you an overview.
They have our next story is they have a new release, version 1.12.1 of NetData, which is a kind of, statistics gathering service daemon thing. They've improved their driver type options for their IPMI integration, support for improves larger sizes of file systems, and lots of stuff. The first time I saw NetData was actually the way it's integrated into FreeNAS, and you can get graphs of lots of different things and find out what's happening on your machine, basically. It's here, they have a good description. A distributed real-time performance and health monitoring for systems and applications. It's highly optimized monitoring agent you install on all your systems or even in all your containers. And then NetData provides insight in real time for everything happening on the systems, including web servers, databases, and applications using highly interactive web dashboards. It can run autonomously without any third-party components, or it can be integrated into your monitoring toolchains with things like Prometheus, Graphite, OpenTSDB, Kafka, Grafana, etc. NetData is fast and efficient, designed to permanently run on all systems, both physical and virtual, containers and IoT devices, without disrupting any of the core functionality of the device. It has relatively good integration with ZFS. I think a bit of it's skewed towards, the Solaris and Linux versions of ZFS, but hey, it's on GitHub, so it's easy enough to fix. There's maybe a couple tweaks I might make to it, but I haven't had time yet. But in general, it's quite interesting and does work on BSD.
Yeah, which makes it interesting enough for us to cover it and have a closer look.
Just like last week, we promised more Chris Seiberman posts. Here's another one.
Yeah, did we actually promise that?
Yep.
Okay.
It was like an hour ago. How do you not remember that?
Yep. So yes, his blog post basically covers an old Unix trick using grep with def null. Yeah, you were thinking, why would anyone grab stuff from def null? But here it goes. Every so often, I will find myself writing a grep invocation like this: find something -exec, grep something, and then use def null with the curly brackets in single quotes, and then another single quoted plus. The peculiar presence of def null here is an old Unix trick that is designed to force grep to always print out file names, even if your friend or if your find only matches one file, by always ensuring that grep has at least two files as arguments. You can wind up wanting to do the same thing with direct one or direct use of grep if you're not certain how many files your wildcard may match. For example, grep something, def null, and then */* a thing and another asterisk. With this particular trick is functionally obsolete because pretty much all modern mainstream versions of grep support /H argument to do the same thing, which is the inverse of the lowercase -h argument that always turns off file names. This is supported by GNU-grep and the version of grep found in FreeBSD, OpenBSD, NetBSD, and Illumos. And to his surprise, -H is not the latest single Unix specification grep. So if you care about strict POSIX portability, you still need to use the def null trick. And he writes he's biased, but he's more sure you would care about strict POSIX compatibility here. POSIX-only environments are increasingly perverse in practice. Arguably, they always were. Okay, but if you stick to POSIX grep, you also get to live without lowercase h. And his usual solution to that is cat. So you cat whatever to grep and then something.
So if you cat 5 files and then pipe that into grep, grep will not think that there's multiple files and prefix each match with the file name because it only thinks there's one input because cat has concatenated them all.
And this is not quite a pointless use of cat, but it's an irritating one. For whatever reason, he remembers lowercase h better than he does uppercase h, so he still uses the def null trick every so often out of reflex. He may know yeah, that grep has a command line flag to do what he wants, but it's easier to throw in a little dev null here than to pause to reread the man page. He's often again forgetting to get that exact option. Yeah, nice trick. And for the people who are not using AWK to do grep-like things. And we also found a nice tutorial of sorts. Yeah, it's a tutorial about using your favorite email program, Mutt, with Gmail.
Yeah, so how to access your Gmail from Mutt, apparently.
Mm-hmm. And
so they go on, I recently switched to Mutt for email, and while setting up Mutt to use IMAP is pretty straightforward, this tutorial will also document some more advanced concepts, such as encrypting your account password and sending emails with a different from address. So after they install Mutt and do their initial configuration, where they're actually accessing Gmail via IMAP, and they set it up. Just going through spool file inbox. Anyway, this tutorial assumes that you are somewhat familiar with using Mutt and have installed it with sidebar support and are comfortable with editing your Mutt config file. But if not, they also provide a GitHub link with their version. Then they show how to encrypt your account password, since this is going to have the password for your Gmail written in your config file. That's probably not optimal. So rather than having that sitting around in plain text on your disk, you can use GPG to encrypt the file, and it'll basically make you enter your GPG password every time you've not used it for more than 5 minutes to decrypt the file and then read the contents. So you can see here, it uses shred, assuming you're using an overwriting file system to make sure the contents get overwritten as well. And basically you make the source for your password instead of a file is actually GPT decrypt the file pipe. And that way your password will be stored on disk GPT encrypted instead of in plain text. And then they walk through how to use Gmail's SMTP service on the alternative port to be able to send email via Gmail so that it'll be signed by Gmail and not get blocked by spam filters as being falsely from Google. So even if you use Gmail, you can hook it up to Mutt.
Problem solved.
Yeah. I know a bunch of people that might actually do this or probably are already doing this.
Yes, this is a possibility. So, time for our Beastie Bits this week. We start off with an extensive Unix timeline. For the people who are still wondering, did my Unix come before that other one, or is this earlier than that? Here is the page.
Yeah, so you see on that page, there's this white bar, and it kind of just looks like it has some random static in it. That's actually the timeline. It's just too big to fit on your screen. If you hover over any in particular part, you can see here we got HP made their own version of BSD back in 1988, just before 4.3 BSD Tahoe came out. And then parts of 4.3 BSD Tahoe went into the MIPS OS. And then you can see later on came 4.3 BSD Reno. And then you can see Sun OS and QNX. And there's the 90s. There's FreeBSD and NetBSD, Junos, Trusted BSD even. And you see NetBSD and OpenBSD coming back together to make MirrorBSD.
Yep.
FreeBSD 5 Developer Preview 2. So this is obviously a very detailed timeline when they include some of the
in-between versions
and stuff. Darwin and macOS and Solaris 9 and 10. All kinds of stuff. And there's macOS High Sierra. Yep. Well, they got QNX going in the BlackBerry. Even have OpenBSD 6.3. Dragonfly BSD. There's FreeBSD 11.2. So this is up to date to at least the middle of last year.
I guess they will keep that updated.
Mm-hmm.
Oh, wow.
And it's available on A4 or letter-shaped paper for a plotter if you want to print a giant version, or there's just an index of the history if you want as another file.
It definitely tells us we've come a long way.
Yep.
And if you scroll down, there's much more links and much more information about some of the Unixes out there. Ooh,
here's just a list of the Unixes, including 1, 2, 3, and 4 BSD, 4.4 BSD, Lite 1 and 2, 386 BSD, Android, Apple TV, Arch BSD, BSD Net 1 and 2, BSD 386, BSD OS, Darwin, Desktop BSD, Mac OS, iRix, iOS, iPhone OS, iPod OS, June OS, QNX, Plan 9, PCBSD, Open Server, Open Solaris, OpenBSD, UCLA Locus, UCLA Secure Unix, and SunOS, TrianceOS, True64, Unix System 3, 4, 5, USG, Venix, Xenix, Xmach, everything's in here.
Yeah, very, very thorough collecting.
They've actually got a list of Unixes they plan to add eventually, including, Zeus, which I think is the one that PHK started with, if I remember correctly from an email signature I read once. Lots of different ones in here.
Yeah, that's a whole archive. Unix history.
Oh, Illumos. That definitely belongs on the chart somewhere. Oh, they have RetroBSD and LightBSD. Those will be an interesting line on the chart because it's like, we just took this version from 20-something years ago and made it work on really small hardware today.
Yeah, well, there's a use for it.
Yeah, and they have links to some other useful stuff, like the creation of the Unix operating system from Lucent, an oral history of Unix from Princeton, Unix Past from the Open Group to people that maintain the POSIX standard, or just FreeBSD release information from the FreeBSD projects page. The history of Solaris, Sun's history, the history of HPUX, Unix and Multics, 20 years of Berkeley Unix by Kirk McCusick. There's a good one. Lots of stuff. Definitely worth checking out.
Yep. And we have some bad news, I guess. Garbage.fm, OEF.
End of file. Yes.
Yep.
So the Garbage.fm podcast has officially ended. I guess not that big of a surprise. They only released like 4 episodes over the course of 2018, if I remember correctly. They only had, or maybe one a month-ish. So they were not managing to keep a very regular recording schedule. And so I suppose it makes sense.
But yeah, thanks to Brandon and to Joshua for producing the ones that you did. And maybe in the future you do something similar to that or with a different name. And so, yeah, this is coming to an end, but maybe something comes afterwards.
Yep. I think it was Brendan did an episode of BSD Now and then really liked it and went and did a podcast. And then very quickly you realize, wow, doing this every week is a bit much.
Yes, it's involving people into it, but definitely end something at a certain point if you don't have the time for it. Otherwise, people are just waiting for the next one without knowing what's going on. All right, then we have BRK to SBRK over at Dragonfly BSD.
Apparently, the system call BRK in Dragonfly has been replaced with SBRK. It won't affect you from an end user perspective other than making sure that you have to upgrade everything during the next release. But it's a system call change, so there's really nothing. It just means you'll have to get fresh binaries so that they use the right system call because the other one won't exist anymore.
Okay, That's good to know.
Then we have, apparently they found stock again. So Tobias Florek has had a soft model made of Fred, the Dragonfly BSD mascot, many years ago. He is moving and found a few unsold units. If you are in Europe for shipping purposes and are interested in having one, then contact Tobias at dragonfly@ibody.net before they run out, and maybe you can get a stuffed Fred.
Oh, take my money, yeah.
Yep.
Cool, yeah. And the next item we have is Caffe. Can OS kernels forward packets fast enough for software routers? Over at the IEEE.
So it is widely believed that software routers based on commodity operating systems cannot deliver high-speed packet processing, and a number of alternative approaches, including user-space networking stacks, have been proposed. This paper revisits the inefficiency of kernel-level packet processing inside modern OS software routers and explores whether a redesign of kernel network stacks can improve the incompetence. We present a case contrary to the belief through a redesign. Caffe-A, a kernel-based advanced forwarding engine that can process packets as fast as user space network stacks. The Caffe neither adds any new APIs nor depends on proprietary hardware features, but the Caffe outperforms Linux by 7 times and the route bricks by 3 times. The current implementation of the Caffe routing system can route 64-byte IPv4 packets at 28.2 gigabits per second using 8 cores of a 2.6 gigahertz processor. Our evaluation results show that the Caffe achieves similar packet forwarding performance to Intel's DPDK while consuming much less CPU and less memory. That's interesting.
Yeah, this is IEEE, but definitely close enough to what people want to run on operating systems. Packet forwarding.
Importantly, it shows that building a router out of a BSD is still very much an option.
Oh yeah, it didn't get old. Speaking of old, there's ARPANET celebrating 50 years since LO. And this is a live stream of sorts, I think.
Yes, it's a live stream, but you can watch the recorded version. So you just click the button and it will run again. So they're celebrating scientific milestones, in this case, the beginning of the ARPANET.
And they have a little transcript at the bottom, so you can see what
October 29th, 1969, saw the first successful intercomputer message transmitted from UCLA on the West Coast to the Stanford Research Institute on the East Coast. It was received as the letters LO. The remaining letters of the intended message, which was log space in, were cut off when the program crashed.
Welcome to computing, everyone.
An hour later, with some system changes, the full message was successfully sent and received.
Other classic computing started right this way.
Yeah. Other institutions joined the network over other years and purposely sent the message LO as the first message. Including the University of California at Santa Barbara, the University of Utah, MIT, and the RAND Corporation.
And from there, the internet started.
Yep. And they have the speakers in the video include Vinton Cerf, who was one of the co-authors of TCP/IP, Stephen Crocker from Shinkuro Inc., Elizabeth Fendler from SRI, and David Walden, who apparently doesn't work for people. He's independent.
Ooh, okay.
Anyway, looks like a good thing to watch.
Okay, after we went through this part, we should cover our feedback and questions for this week. Remember, if you have any questions about BSDs or something you always wanted to ask us, then send this to feedback@bsdnow.tv to cover it in a future episode.
Yes, please. Need lots of questions.
Yes, Pablo did this, for example, with a topic suggestion he had for example, FreeBSD on a laptop as a daily driver. Yeah, we get this a lot. He writes, hello there. I really like your show, and it actually got me started experimenting with FreeBSD on a separate partition of my laptop. Hey, that's nice. I'm learning a lot. Even better. So as you always ask listeners to submit questions and suggestions, perfect tie-in here. Here is mine. Even though I might not be that much of an advanced topic, that's fine, as the others covered in your show. So the question is here, what is your experience with BSD as a day-to-day, all-around OS for your desktop and laptop?
So is it usable? Yes. So the workstation I sit at work 4 days a week, because I take Wednesdays to do the show, that machine only runs FreeBSD. There's no other OSs installed. I also don't even have any VMs on it. It's just FreeBSD. Main applications I use are the terminal and all the FreeBSD apps that way. My chat client, Quazzle. I use the same chat client on Windows, FreeBSD, Mac, and my phone even. It runs Thunderbird and Firefox for email and website stuff. Yes, I do 100% of my work on that computer, other than the odd time where I need the Java silliness for IPMI or something. We have a Windows computer in the corner, although I could do that just as easily with a VM on the machine. It's just faster to go to the other computer, in our office. So I also use FreeBSD on my laptop, like my X270 that I take to conferences. Same thing, very usable. So to answer your question, how do you rapidly manage Wi-Fi's? I actually use the PCBSD Wi-Fi manager that is in the FreeBSD ports tree. So there's just a port. It gives me a little Qt app that can scan and select all the Wi-Fi networks. And it's basically just as easy as switching Wi-Fi's on my Mac. So you can't really get any easier than that. Common applications that you might miss. I don't know. I don't use that many anymore. I don't really use Skype as much as I used to outside of the podcast. And they have the web-ish version now. So if all you need is instant messaging, or I guess even some level of WebRTC-based calling,
there's a lot of alternatives, and yeah.
Yeah. I'm not sure what common applications you might miss because I don't know what you normally do with your computer. I mostly use cross-platform apps nowadays. Almost all the apps I use the same app on my FreeBSD laptop, my FreeBSD workstation, my Windows gaming computer, and my Mac travel computer.
Yep.
Problems you run into? I don't know. A lot of problems that you might run into are papered over for me by the fact that I've been using FreeBSD for 20 years now and I've been a developer for a while. I kind of don't notice some of the hiccups because I can always get myself out of the hole.
Yeah, but as a beginner, you have definitely a learning curve, but that shouldn't turn you completely away from it.
But again, it depends on your use case. Like if the main thing you're doing is running, your email, visiting websites with your browser, and a couple other applications that are cross-platform or something, then the OS doesn't really matter and just gets out of your way. Whereas if you're doing something more specific, you might run into gotchas. Advantages over Linux. Mostly, I know where everything is and what everything does, and things don't change on me unexpectedly. I also like being able to update the OS separate from updating the applications. So I can update my packages to get a newer version of Firefox and know that it's not going to change anything in the operating system. Or I can update the operating system without having to download the latest version of a package.
That's still separate.
I can separate those things, and with boot environments, I can undo them. Really important for my work computer. If I decide to upgrade on Friday afternoon, I don't want to have to spend the whole weekend getting the machine working again just so I can do work on Monday. I know that if I totally screwed up, I'll just reboot on Monday and select the machine worked on Thursday, and I'm back to doing work without having lost anything. Configuring BSD on a laptop in particular, I didn't have to really do anything on mine. I did some minor tweaking with the way I like the touchpad to work. Like I like to disable tap to click because I have the actual mouse buttons on the Lenovo and I prefer to use those and be able to drag and stuff without it trying to click. There was a little configuration to control the screen brightness with loading the ACPI_IBM module or whatever, but it wasn't anything special. So power
many things
usage,
are supported.
The CPUs do a lot of this outside of the OS now, but you can use something like PowerD or Power++, or whatever it's called. Because the X270 I have has 12 plus hours of battery life, I can easily get at least 9 or 10 of that under FreeBSD, and so I've not really had to think about it. And then, the biggest draw on your laptop is almost always going to be screen brightness. So, that's part of it. Also, it helps that the newer CPUs, like the Kaby Lake in my X270, is an up/down TDP. So when you run it below 1.5 gigahertz, it only takes 6 watts. Above that, it only takes like 15 watts. But if you kick it into the turbo boost, then it uses 26 watts. So you can use PowerD or just the dev.freak or dev.cpu.0.freak for frequency to decide what speed you want or what you want the upper and lower bounds to be. And if you just say never go into turbo, then you're never going to use more than 15 watts and you'll get at least this much battery life no matter what. Although sometimes going into turbo for 2 seconds to finish the work in 2 seconds instead of 5 might actually save you more battery life.
Yeah.
But I've not had a problem. If you sit there doing Build World on your laptop all day, you'll run the battery down pretty quick. But outside of that, I've not had any real trouble. And is it a good idea? I don't know, but I do it every day.
Yeah, your usage might differ, but it's worth trying out. And then you see, this is missing, or I need to ask about this other thing. Maybe I find something on the internet, or hey, this is actually quite nice as a work environment.
The other thing I'll say is at work, every one of us uses FreeBSD, even the people who aren't FreeBSD developers. So like even our co-op student, so is a college student, had maybe used a little Linux and had tried FreeNAS once before. We brought him to the office and sat him down at a FreeBSD machine with Lumina and KDE or something installed, and he just sits there and does his work every day. And really, the OS doesn't get in his way because he needs email, the web browser, and a terminal to run SSH and command line stuff from, and some basics like that. So it doesn't bother him at all.
There are a lot of familiar things in each operating system that you just immediately recognize. It's
to the point where I could replace the OS on my mom's computer with FreeBSD because it's got the web browser, the email, and that's pretty much all she does. And she would just never get a pop-up about Windows Update ever again.
That's a good reason for switching.
Exactly. So yes, FreeBSD spends a lot of work on being good for servers and so on. It is a general purpose OS. And, if you look around at a BSD conference, at least half the developers there will have a laptop running BSD. Some of them you'll even be able to tell because they will have these nice stickers that Worm Block made for us.
Yes, the dog food stickers.
Food stickers. You get these by actually running FreeBSD on your laptop at the conference, and as it says, eating our own dog food. So yes, most FreeBSD developers do actually run FreeBSD on their laptop. I will admit a bunch of them may also have a Mac that they use for, teleconferences and video calling software and stuff that they have to do. But it's more just...
They have all kinds of shells running in SSH into FreeBSD boxes, and
I do all my development not on a Mac, but sometimes especially when I'm traveling, if I need to make a video call or whatever, it's easier to just open my Mac and leave my FreeBSD computer running instead of having to reboot it or something, or just mess with WebRTC and stuff like that.
Yep. So yeah, if you're coming from Linux and are used to the i3 window manager, then that's available on the BSDs. Just like you can basically just copy over your config file even from your home directory, and it should just read that as it was on Linux. So no new or surprising things there. And from there, you just look what you need and what's different. And there's a lot of information out there, and people are happy to answer your questions.
Yep.
So I think it's worth trying this out, and I think you should be able to make a lot of progress.
And, if you run into trouble, email the show and we'll see if we can have some advice for you.
Yep. Okay, so thanks for writing in. And next one is Ron about ZFS on the fly compression and seeks. This goes, hi, first off, thanks for your work on this podcast. I have found it to be very useful source in his transition towards running FreeBSD as his primary operating system. Hey, great. In episode 277, Kogoman asked a question that involves rotating a set of SSDs to prevent all of them hitting a write limit at the same time. A fairly simple solution for this would be to buy 3 SSDs, set of 2, set them up as mirrors, and say 6 months later attach the third to create a 3-way mirror where one drive, which will mean one drive will have fresher flash, gaining the potential benefits Cogman desires with being simple, as well as gaining the benefits of a 3-way mirror over a 2-way. You could even buy the third later and be more or less certain the third is from a different batch too.
Yep. Or when you add the third one after it's resilvered, you could remove one of the other 2 and set it aside to add back later. And then you would get, the different ages. But
yeah, and so for
there's lots of ways you could do it. It's not, there's not one particular way that's necessarily better.
Yeah. But yeah, think about it ahead of time before you're buying a lot of disks that you don't need necessarily up ahead. So for his actual question, when using on-the-fly compression on a dataset containing some large binary files, in his case a set of binary records where each entry is of fixed length, is the ability to seek to an arbitrary point, like the nth entry, by translating the offset to a particular sector, or does the compression mean that all accesses to these files become effectively streaming reads over the entire file to find the data at the relevant offset?
So ZFS still has its record size. So no matter how big the file you're compressing is, ZFS takes 128K of uncompressed data by default. That's the record size by default. So it fills up one record with uncompressed data, then compresses it and writes it to disk, and then does the next one. So if you have a 100 megabyte file and you're seeking to the 10th megabyte, it just knows, okay, that'll be in the 80th record. And at most, it will have to read 128K. To find whatever you're looking for in that file. So you would only read one record or 2 if your read happens to span or something. But so it doesn't have to decompress everything because the file you wrote will be broken up into blocks of the record size and then compressed. So if your file compresses 2 to 1, then every 128K of your file will only be 64K on disk. And it will save a bunch of space. But when you seek, it will seek to the actual size of the file, like the logical size of the file, figure out what sector that is, read that chunk, and then decompress it. So you won't have to decompress everything.
Yep, only the bits that changed.
But because of the checksum and so on, you have to read the whole record anyway. To verify the checksum, so there's no real disadvantage. Plus, we put the whole thing in cache, because if you seek and read the 10th megabyte of a 100 megabyte file, the chance that you read, the next 128K after that is pretty high. And now ZFS will already have that in memory, and you will get even better speed.
Yep, because of caching and all that.
Yeah. So it's not quite perfect, but it's also a lot better than it would be if you treated that entire file, compressed the entire file and wrote it to disk, and then had to decompress it to figure out where the 100th megabyte might have actually been compressed to, especially since compression will vary over different parts of the file. But because the records are broken down based on the actual size of the data before it's compressed, it means that when you're seeking to a specific location, you'll only have to read the records related to that location. It just means to read the 128K that is that record, you'll only have to pull a smaller amount off disk because it was compressed.
Yeah, and that pretty much covers.
This is why sometimes using a record size of 1 megabyte is better, because the bigger the chunk of data you have, the higher the compression rate you might get. But it does have the downside here, and that's why for databases, we often recommend that you use a smaller record size, like 8 or 16K, that matches what the database uses. Right? If the database always reads or writes 16K, like MySQL does, then making that your record size means that when it overwrites one chunk of its database, you don't have to change the middle of some other file or whatever. It's just literally the part of the file that you wanted.
Yeah. So yeah, different use cases, but ZFS is flexible in that regard, and you don't have to worry about, I have a fixed block size. No, not anymore. And that gives us a huge benefit in the compression area. All right, let's go to our last question. And this is to pool or not to pool or Z-pool. This is the question. And here goes. Happy FOSDEM, folks. Oh, it's been this beginning of this month, remember, Alan? But now we get this greeting now. Okay. So whether 'tis nobler in the mind to suffer the slings and arrows of outrageous performance, etc. Footnote. Excuse the misquote from Hamlet, I beg you, good sirs. Methinks a tale of two pools would have been a better choice. Yeah, probably. So he has a fast NVMe disk, yay, and a large slow, by comparison, Z-pool of a striped mirrored SATA disk, or disks. Suddenly, these are separate Z-pools. Day-to-day work, including source ports and jailed stuff, runs on the NVMe, and the archive pool is used for longer-term storage and further databases, Beehive and jail torture. The system runs 12.0 release, patch level 2. There's patch level 3 out, so you do, you know.
Probably not when the email came out, though.
Yeah, right. And has plenty of RAM. Okay. So doing large ZFS reads, like ZFS send to dev null, has a naive benchmark. The NVMe drive does a leisurely 1,400 gigabits per hour, like 400 megabytes per second.
1,400 gigabytes per hour, yes.
Yeah. And the disk Z-pool does around 700 gigabytes per hour with 200 megabytes per second. Sends roughly half of the throughput of the former. So the NVMe drive is faster, definitely. It's already far faster than my day-to-day needs, but quite a margin, but it's not as fast as he's expecting it. Am I missing some secret FreeBSD tunable? Am I simply a victim of lying, deceitful vendor market droids?
So you might want to use NVMe CTL, or sorry, NVMe control. If you read the man page for it, it has some benchmark stuff in it that's a little more tuned for NVMe. Be careful. Don't do the write benchmarks, as those are destructive and will write stuff all over your disk. Just do the read ones, and you can see there. So ZFS is tuned by default more for hard drives. And so the big difference between an NVMe and even just a SATA SSD is that with NVMe, you're not speaking the SATA protocol, which is designed to for disks that do one thing at a time, right? You have one head, you move it to a location, you read, and then you move it to the next location. SATA has an algorithm called native command queuing, which is when we get a whole bunch of commands and the hard drive takes them and can sort them and do an elevator algorithm to, if I'm going by that spot, I might as well stop and pick up that data on the way, kind of thing, to optimize that. But it still does one thing at a time. With Flash, that's actually kind of a disadvantage because generally an SSD is made up of a bunch of separate flash blocks that can each do one thing at a time, all kind of meshed together. So with SATA SSDs, sometimes you want to queue up more commands so that internally the drive can actually do more. Normally on a hard drive, you don't want to queue up too many commands because you're forming a line of these commands and they take, turns, like a queue at to get into a movie or whatever. If the queue is too long, when an important thing joins the end of the queue, it has to wait till all the less important stuff in front of it gets done before it gets a chance to use the drive. So ZFS, for example, with read-ahead reads that aren't important, we're just doing it because it might get asked for later, and it'll be good to have it in memory, only lets one or two of those be queued at a time. And then, writes we can let up to 10 or whatever. But it's so that when an important read comes up, some applications waiting for this read, we have to do it as soon as possible. It means that hopefully there won't be more than 3 people in line in front of it. If we then change that, so there's 32 people in line in front of it, it's going to take a lot longer before that read gets its turn to use the hard drive. With NVMe, the protocol supports up to, I think, 65,000 commands at once, although most devices nowadays only support 64, but the spec was written for the future. So that means that an NVMe device can usually execute 64 commands at once and have them complete out of order and so on. Much more advanced protocol. That's the reason why we have NVMe instead of making it all use SATA. And also, usually on NVMe, at least one of those 64 command channels is reserved for admin commands so that they will never have to wait in line. Anyway, to take advantage of an NVMe, especially with ZFS, you probably want to turn those queue depths way up. So that ZFS will send a lot more commands to the disk, since it turns out the NVMe disk can do 63 of those commands at once. So if you're not queuing at least 64 of them, then one of those queues is probably doing nothing. The problem is the tunables for that are system-wide. So if you tune it up for the NVMe, it's also going to tune it up for the hard drives and make your hard drives perform more poorly. This is a problem that I've been working on. I gave a presentation at the ZFS Developer Summit about per VDEV properties, where we could move some of these tunables from being system-wide to being at least per pool, if not per disk, or at least VDEV, like a per RAID Z set or whatever, so that you would be able to have a higher queue depth for NVMe without having to turn up the queue depth for your spinning hard drives, because people having tiered storage where they have 1 or 2 or 3 or even 4 different speeds of storage in their system is becoming more and more common, and ZFS needs to support that better.
Mm-hmm. Okay.
Yes. So question 0, can you go faster? Probably. The NVMe control command will use multiple threads and multiple concurrent commands and give you a better idea of what the performance is. And then you can vary a bunch of the settings there, like the block size. It's actually, I was helping Dan Langille do this with the NVMe he got this week earlier in the day. And he found that, he got different speeds depending on if you use 512-byte blocks, 4K blocks, 8, 16, 32, or 128K. And then also varying the number of concurrent threads that were issuing commands affected the performance as well. And you might be able to see what's up there. Mm-hmm. Also for reading, having multiple devices, especially, I think you said they were mirrored, your existing mirrored SATA drives. When you have 2 machines doing the work, you can get much better speed. Spinning hard drives can get somewhere between 100 and 175 megabytes per second. You have 2 of them and you're doing linear reads, you can get pretty high speeds. If you're doing random reads, the hard drives will get a lot slower suddenly, and it turns out that your NVMe might actually be, 100 times faster than the hard drives at that, but not necessarily at sequential reads. But yes, I would expect more than 400 megabytes per second, depending what you're doing. If you're reading just 512 bytes at a time, I think the NVMe Dan had topped out at like 120 megabytes a second. Because even then, it was doing 280,000 IOPS, because you're reading half a kilobyte at a time. If you have it read 4 kilobytes at a time, I think the relatively cheap one Dan had, with 4K sectors, he got up to 850 megabytes a second. And we went to 40 kilobytes reads at a time. He was over 3 gigs a second.
That's significant, yeah.
Yeah. And so you definitely want to check what the record size, or like the physical block size you're using on the NVMe device. But most likely it's just a matter of queuing and so on. But try out the NVMe control read-only benchmark, and maybe some other tools you might know of to try to figure out what the NVMe can actually do, and that'll give you a better idea of how you might tune ZFS to take advantage of that. The downside is the fact that you're going to the system-wide tuning means it's going to impact your SSD, your spinning disk pool, and so you probably won't be able to tune it quite as much as you would hope.
And what about his other question? How does having two Z pools impact the ARC and other ZFS internals?
So you have one ARC. Your ARC max specifies the size of it, and all the pools share it. ZFS was built to be able to have thousands of pools if you want. It kind of defeats the point of ZFS, but it's perfectly allowed and works well in these cases. If you want one of the devices not to use the ARC as much, you can change the primary cache property to say metadata, and it will cache only the metadata, not the actual data, if you want to force more of the ARC to be used for the other machine.
And so this way you can copy files between the pools, and it will already remain in cache or be in cache in ideal situations. Okay, I think
and then he had
covered the rest.
Number 2,
mostly. Oh yeah, might there be any advantage to using some of the NVMe drive as a write-ahead cache for the larger disk-based Z pool? I don't see any advantage in adding the whole 1 terabyte NVMe drive to the Z pool. It would be a waste.
That mostly depends how many synchronous writes you're doing. If most of the stuff on your spinning drives is, jails and SVN and stuff like that, that are not doing synchronous writes, then it probably wouldn't make a difference. Because it's only going to, if you create a slog, a log device in ZFS, it's only used for synchronous writes, not for asynchronous writes. So only writes where the application says, I'm going to sit here and wait until you tell me this is safe before I continue. Things like databases do that. If you don't have a lot of that, then it's not going to help. If you are going to partition it, you probably don't want more than 16 or 32 gigabytes for your slog. So that would leave lots of your 1 terabyte NVMe for your separate pool.
Okay. And last question there. How can I tell if the NVMe drive should use 496 or 4K byte sectors or 512 byte ones? The drive reports 512 sectors like all lying storage devices of modern age. Yeah.
Just because, again, your limit might actually be IOPS and transaction speed, the bigger sectors is probably better. Some devices actually let you reformat the drive and change the native sector size with the NVMe control utility. But of course, that's reformatting the drive, among other things. I don't see any reason not to use 4K sectors for pretty much everything nowadays, unless you have an extremely huge number of really small files where maybe the slack is going to add up on you or something. But you'd have to have probably, on the scale of billions of small files, not an SVN checkout before it would make a difference.
Yeah. Okay, that was going very deep into the pool. But as NVMEs become more and more commonplace, then people are prepared to use it properly with ZFS.
Yes, I'm hoping to have more time to work on the VDEV properties stuff because I'll be presenting a bit about it and about tiered storage at the ZFS user conference in April. So check that out. If we'd love to have more people from FreeBSD come. So it's zfs.datto, datto.com. And check it out. It's in Norwalk, Connecticut, which is very close to New York. And I hope to see lots of people there.
Yep. All right. Thank you for listening to this episode of BSD Now, and see you next time.